All right, welcome back, class. So today we're going to reflect a little bit on the calculations we did last time. Namely, we've got in our hands this neat trick of computing partition functions for systems that are non-interacting, so whose energy can be expressed as some linear function of single particle energy functions. And in that case, the Boltzmann distribution tells us that those particles fluctuate independently, and so one needs to only enumerate the microstates associated with a single particle, and therefore get access through the factorization structure of the partition function for a non-interacting system, the total capital Q partition function. And we've done these calculations for a couple different concrete systems, gases, whereby particles have only translational motion. We did that both classically and quantum mechanically. Additionally, we considered harmonic oscillators, also classically and quantum mechanically. And in both, we found an important result, which is that in a specific limit, those calculations were consistent with each other. So we're going to review those findings briefly here in the first 10 minutes or so. We'll go back over that very important notion of statistical independence of position and momentum, which comes about classically. We'll consider again those harmonic oscillators kind of in nature in the context of extended solids. And then we'll wrap up today's lecture playing a little game I like to call the heat capacity game, whereby we try to see if we can actually compute quantitatively the heat capacities for some simple gases. Okay, but let's start with a bit of a review. So we have, from last time, identified single particle partition functions. Under cases of fixed number of particles, volume, and temperature. So these are the canonical partition functions. And a couple key results that we've arrived at, for example, in the case of a classical system where particles only translate. So we have an energy, which is just kinetic energy, say in one dimension for simplicity, confined to some constant volume, in this case a one-dimensional line of length L. That single particle partition function, denoted little q, was just L in some units of a discretization, some resolution we had to introduce in order to count a continuous variable. Similarly for the velocity, we had to introduce a resolution, and we found that the temperature dependence of this partition function was such that it went like beta to the -1/2. In fact, we thought about a little bit how do we interpret this result? How do we understand this number of thermally accessible microstates? And one of the nicest ways I think there is to consider it is to just think about that we've essentially just counted the number of places I can put a particle on a line in some temperature-dependent length scale, or within some temperature-dependent unit, the thermal wavelength. So again, knowing the temperature dependence of the partition function is useful because we know that we can take derivatives and get average energies by only knowing that temperature dependence. We contrasted that result with the quantum mechanical result. For a particle in a box, the energy function, in this case the energy eigenvalues, are distributed with a quantum number n, goes like n squared with numbers out in front, factors of Planck's constant h, the mass of that particle and the length of that box. And in the high temperature limit, where those energy gaps were much, much lower than kBT, we could compute this partition function and arrived at L by H, a factor of M, and the same factor of 2 pi beta M to the 1/2. Indeed, the temperature dependence also entering in as a factor of beta to the -1/2, meaning that the average energies for a quantum or classical particle in this limit are the same. We actually use this calculation to argue that maybe a reasonable resolution, a reasonable factor of this delta x delta v could be informed quantum mechanically as a factor of Planck's constant divided by m. It's essentially a restatement of Heisenberg's uncertainty principle, saying that it really doesn't make sense to specify a unique microstate on scales lower than that uncertainty implied by quantum mechanics. Okay, so this was one example of a isomorphism between the quantum and classical result in the appropriate limit. It's not sheer luck. In fact, we showed that if we considered a harmonic oscillator, so an energy function classically, where I also have kinetic energy, we did this in momentum variables instead of velocity variables. Harmonic oscillator has a potential, which can be written as an effective spring constant m omega squared times some displacement from the bottom of that spring, denoted as x squared. That partition function, again, in this one-dimensional system was 2 pi, some artificial resolution in x and v, or p, sorry, and a factor of beta omega. Again, finding that there was a simple beta dependence, it went like beta to the -1. We could do the quantum mechanical result, in this case, exact, in an exact way. We didn't have to first go to some high temperature limit, owing to a special feature of the form of the partition sum for a harmonic oscillator being a geometric series. So the energy function for a quantum harmonic oscillator have constant energy gaps of scale h bar omega and some principal quantum number n that sets which eigenstate the system is in. Evaluating that partition function, we got some complicated hyperbolic trig function, in this case sinh, whose argument was beta h bar omega by 2, and this was all inverted. But what was interesting is that in the high temperature limit, we found that this went like 1 over beta h bar omega. So in that large temperature limit. Exactly the same temperature dependence as the classical results, and using that same information that maybe we should choose a scale for resolving microstates as that suggested by quantum mechanics, we find consistency again. So that's a real quick rehashing of those specific calculations. There were two kind of big takeaways from those calculations. One is that there's a sense in which a classical limit can be obtained when the thermal energy scale, at least from the perspective of counting microstates, when the thermal limit, or when the thermal energy scale is much, much larger than any relevant energy gap. The kind of physical picture to have in mind there is that the fundamental difference between quantum mechanics and classical mechanics with respect to evaluating their partition functions is whether or not the energies are continuous variables or discrete variables. When the thermal temperature is much, much larger than any energy gap, those discrete levels blur into what is essentially a continuum. in which case it's then not so unexpected that you do get the same result. Another point that has come out of the classical calculations is this continued dependence on beta as some simple fractional power entering into the partition function, implying a simple functional form for the average energy and therefore the heat capacity as functions of temperature. And we gave this a name. We called it the equipartition theorem. Which was a consequence of us considering simple harmonic forms for the energy, whether or not this is the potential energy in the case of a harmonic oscillator, or the kinetic energy generally. When we have a classical system whose degrees of freedom are independent and obey Gaussian statistics, so enter into the Boltzmann factor as a quadratic function. All instances of this behavior, anytime I have a Boltzmann factor that looks like a Gaussian, if I can treat that variable independently, and it is a classical system, I can integrate that Gaussian, and I will find every time that each one of those variables contribute 1/2 kBt to the average energy. And consequently, 1/2 kB to the heat capacity. So essentially, anytime you find a quadratic form to your energy function, you know what the answers are going to be to relevant questions like how do they contribute to the average energy. Okay, so one can show that pretty simply. We've shown it somewhat implicitly in our discussion of the specific cases of translational and harmonic motion. And so these are, I think, the two major takeaways. One additional important insight we've gleaned in considering classical systems is this notion of the statistical independence of velocity fluctuations from positional fluctuations. So I want to talk about that a little bit more. So most molecular systems have energy functions that can be written down as some potential energy part and some kinetic energy part. So here's a potential. It depends on where particles are. This, by contrast, the kinetic energy depends only on the particle's velocities. That linearity, the fact that the energy is decomposable as a sum of those two contributions, classically means that when we write down the classical partition function, say using units of resolution informed by quantum mechanics, so we get 3n factors of Planck's constant, we have all of these 3n integrals for all of the 3 cardinal directions that n particles can explore. And we can localize the potential energy piece to that specific integral, set of integrals. and distinctly separate out then all of the velocity integrals weighted by the kinetic energy, which is a function only of those velocities. So we see this factorization of the positional part and the kinetic energy part, the velocity part. And this kinetic energy, velocity part, is something we always know how to do, because the kinetic energy classically is always written down as 1/2 m times the modulus of the velocity of the ith particle, summed over all particles. So the kinetic energy is always decomposable into individual particle pieces. Velocity fluctuations are always uncorrelated, independent variables. Consequently, one can take this integral over all in velocities, decompose it into an integral of the velocities of particle 1 weighted by its contribution to the kinetic energy, separable from the integral over the velocities for particle 2 weighted by its contribution to the kinetic energy, all the way up to the nth particle, moreover, each one of these spatial degrees of freedom, if I have a modulus, that means Vx squared plus Vy squared plus Vz squared, which means that not only are the particles independent, but the Cartesian coordinates with which those velocities fluctuate are also independent. So I can further factorize this vectorial integral over an integral of the Vx contribution to particle 1's velocity times the contribution from Vy times the contribution independently from Vz. And all of those integrals yield the exact same factor of 2 pi over beta m to the square root of. So there's a lot of integrals there, but each one of them gives me the same result. And if I wanted to fancy up this model, imagine that I have different particles. The only thing that would change is what mass enters into those factors, which means that this whole partition function takes on a pretty simple form. I have three n factors of this 2 pi over beta m to the 1/2, multiplying then what is probably a very complicated set of spatial integrals, if that potential is itself complicated. Now, this little volume element that has 3 n components to that space, so that's a 3n sphere. It has units of length to the 3n, so it must be, and indeed it is, that this factor here can be written down as a length unit, depending on temperature, 3n factors of. So we have an effective resolution that comes in even for a complicated interacting system. This factorization of the kinetic energy implies, for example, that the probability of observing the velocity of one particle is completely independent of all the other particles and completely independent of the spatial degrees of freedom with which those particles are moving. So independent of all other degrees of freedom, the probability of observing particle 1's velocity is just its Boltzmann factor for that kinetic energy contribution over the normalization constant for that 1 degree of freedom, which is just then 1 factor of this 2 pi beta m square root of. So that is independent of all other velocities and all spatial degrees of freedom. Indeed, this realization of the simplicity with which velocities fluctuate results in it having a well-known name. This is the so-called Maxwell-Boltzmann distribution of velocities. Boltzmann, because it employs Boltzmann statistics, Maxwell, because he was the one who worked this out the first time. It is just a Gaussian distribution. So if I look at one component of this velocity of a tagged particle, it would look something like this. It would be a Gaussian, so it has a peak at 0, and it has an effective size or effective width to that distribution. Call that twice sigma, which is equal to twice kBt over m square root of. So as the temperature increases, it's not that the average velocity changes. The average velocity is always 0, but the typical fluctuation in the velocity increases. The velocity squared increases while the mean velocity remains identically 0. So again, this should be true for any classical system, irrespective of how it's interacting, irrespective of what sort of state of matter it might be in, etc. So in fact, this is a pretty bold claim. We've explicitly evaluated this for kind of simple gases. I think it's worth actually seeing that this is in fact borne out. So we know how we could check this. We can check this explicitly by comparing to molecular simulation. We can cook up a very simple model of particles and their motion. If it's classical, they obey Newton's laws of motion. And irrespective of how they interact means that we should be able to cook up any interaction. So let's just imagine that those particles just take up space. So they're essentially billiard balls moving around in some box. Okay, so I've coded up such a system, essentially billiard balls moving in a box. So let's play that out. So let's start by, so it's going to be easiest to represent this in 2 dimensions. So these are not actually billiard balls, these are hard disks. I'm going to initialize them in some array, some arbitrary initial conditions spatially, and with some distribution of velocities to start with. And then we're going to see what can happen. So this is just to begin. Let me go ahead and run this. Just written in some simple Python code, integrating Newton's equations of motion. So there's a pretty dilute system that I can evolve. And you see, if you watch a given particle, that those particles move in straight ballistic lines until they bump into another particle, in which case there's an elastic collision that scatters those particles off of each other. So you'll notice that some particles are going very fast until they bump into someone else. Other particles are moving pretty slow until they're rammed into by one of those fast moving guys. Okay. All right, so that's that simulation. Now let's actually test that hypothesis explicitly. So I can, as I evolve that simulation, as I integrate those equations of motion, I can ask for what the velocities of those particles are. That's how fast they move over some time. From that, I can then make a histogram, and I could evolve that histogram in time and see if it agrees with our expectation, this Maxwell-Boltzmann distribution or this Gaussian distribution with a characteristic width set by the temperature. So all things here are known. I know the mass, I can set the temperature, KB is just a constant. Therefore, I should be able to predict what the width of that distribution is. So we'll see a histogram evolving, set up the exact same system, it's dilute, will look like a gas where we know from an explicit calculation that this should work. All right, so let's send it off. You see on the left the probability of some x component of some tagged particle's velocity as a function of that component. The dashed red line is the expectation from the Maxwell-Boltzmann distribution. And we see that, it doesn't really agree really well initially, but as we evolve this longer and longer in time, you might convince yourself that it really does seem to converge to that distribution. Now, why might it converge rather slowly? So how does a particle actually change its velocity? It has to run into something, right? The only things to run into here are other particles. I haven't said, but I've done it. I've made one little trick that makes this gas act a lot like a bulk gas rather than a small section of a gas that I can represent, in that I have opened this system up such that particles going through one side, say the right boundary, are re-inputted into the left side. So I have so-called periodic boundary conditions. So there's no walls on the top, bottom, left, or right regions or boundaries of this box for them to run into. So they really can only run into each other, and they run into each other rather seldomly because this is a dilute system. So it takes a while for it to equilibrate, but nevertheless, after a pretty short amount of time, we say that there's a pretty good agreement between the expected Maxwell-Boltzmann distribution and what we've just empirically measured from the simulation. Okay, but this was still for just a gas. So those skeptics among you might say, well, we proved it explicitly for a gas. Maybe I don't believe that it should work for a dense system, something more like a liquid. Maybe there's something that, some wool I've pulled over your eyes such that that's not valid. So we can set up a much higher density state. So I'll make the characteristic length much smaller so that the same amount of particles are in a much smaller volume, thus increasing the density. So you can see that those particles are much closer together, will look much more like a liquid. And as I evolve them in time, not only do they agree with the Maxwell-Boltzmann distribution, they converge to that Maxwell-Boltzmann distribution much, much quicker. That's a consequence of the fact that those velocities get redistributed really quickly in such a dense system because I don't have to wait so long for the velocity to change because I run into things very, very often. Okay, now if you're really skeptical, you might say, well, maybe I've done something clever with my initial condition. You can see how they are distributed spatially to begin with, but they have to have some velocity, otherwise they wouldn't move. So maybe I've cooked up some very special initial condition for the velocities that generate this Maxwell-Boltzmann distribution. So to just put a nail in that coffin, let me start a system where I put all the initial velocities in just two of the particles. So these two red particles here have all the initial velocity. I'm going to kick them off and watch what happens. Isn't that crazy? They so quickly collide with other particles and so quickly distribute that velocity that within a few integration steps, this system looks no different than the system that started with a more uniformly distributed set of velocities. And still, even though I've started in this very precarious, very unlikely initial condition where all of velocity in the whole system is localized on two particles, I nevertheless, after a fairly short amount of time, reconverge to that Maxwell-Boltzmann distribution. So I find this really cool. Now, there is one more thing that one should consider a little bit, which is if I really am integrating Newton's equations of motion, what do we know about the energy for Newton's equations? It's conserved. So this system is actually a system at fixed energy, not a system at fixed temperature where we've derived these results from. So how is it possible that we've got a constant temperature result from a system that conserves its global energy? Well, we've already seen a handful of examples of this notion of ensemble equivalence. If I have a big enough system, the way that I ask the question, whether or not I conserve the energy or conserve the temperature, shouldn't matter. In fact, what is striking is just how well that works on relatively small system scales. So there is only something like 64 particles here. Nevertheless, it is able to act as its own bath to redistribute energy in sufficiently flexible enough way that it can act like a Maxwell-Boltzmann, act like a system at constant temperature and thus obey Maxwell-Boltzmann statistics. Okay, so that's that. Now let's go back to the formalism in our lecture. So that's where we are with respect to kinetic energy fluctuations. In fact, that's the end of the story. There's nothing more we can really learn about the velocity degrees of freedom for a classical system. They will always obey that Maxwell-Boltzmann distribution. So it behooves us then to try to think about systems which have interactions, but which are still tractable to study. And so that led us last lecture to consider systems that were harmonic, like low temperature solids. So the rest of this lecture is really a discussion of how we can approximate realistic systems through simple models. Essentially a set of applications in which we can work out quite a lot of information of practical importance, like predict measurements of, say, the heat capacity of fairly complicated molecular systems. So let's begin with reminding ourselves of how this discussion of low temperature solids went. So low temperature solid, this could be a crystal where I have some ordered arrangement of particles, say on a lattice. This is just one small piece. This continues indefinitely. This would be an example of a crystal. I could denote the particle position, say the ith particle position as some r vector. I could also, however, have in mind that this is not, that this low temperature solid is not a crystal, but a glass, something amorphous. In either case, if the temperature is low enough, I expect that the positions of particles to be fairly small, to make fairly small excursions away from their minimum energy configuration, or at least their locally minimum energy configuration. let's denote that locally minimum energy position as our vector of I naught. So if at low enough temperature, R does not change a lot, even though the potential energy of this system, which depends on the position of all particles at some time in principle, and thus is likely a very complicated function. Imagine those particles have charge, or even if they just interact with dispersion interactions, this is a very complicated potential. Yet, if the excursions from this average position are small, owing to the low temperature, I could imagine that this potential can be expanded about those typical positions. If it's a stable solid, the first order derivatives go away. And so the first non-trivial term, apart from this constant here, would be a sum over all displacements of the ith particle times displacements of the jth particle with a matrix of mixed second derivatives, which essentially tells you how the potential energy increases due to those displacements. So for concreteness, this delta Ri is equal to the instantaneous Ri vector less its typical position. And this is a matrix of spring constants and thus pretty complicated. Nevertheless, as we discussed last lecture, this matrix is symmetric, so it can be diagonalized. If it's diagonalized, there's a set of eigenvectors, denote them C alpha, or so-called modes that are independent. Which are made up of linear combinations of those displacements. Which means that I can rewrite the total energy as now represented through a linear transformation is as a function of those normal modes. So I need to sum over alpha. There will be a kinetic energy term associated with that alpha mode, and additionally a potential energy term owing to that linear transformation. Now, how many terms are in that sum? So I started with 3 n particles. I started with n particles in 3 dimensions. I've just done a linear transformation, so I still have to have 3n degrees of freedom. I don't add or lose information, I've just rewritten it in a convenient way. And if there are 3n quadratic variables, then classically, as we discussed, equipartition theorem tells us immediately that the average energy is just there are 3 in terms of the sum, but there's 2 terms in those parentheses, so I really have 6n fluctuating variables, so I have 6n contributions to equipartition, each of which come in with a factor of kBt over 2, and thus altogether the average energy is 3n kBT. Taking a derivative of the energy with respect to temperature gives me the heat capacity, which is just then 3N kB. And as alluded to last lecture, this is known as the so-called Dulong-Petit rule. Empirically observed for most solids at high enough temperatures. And to remind you that this was at odds with the experimental observation if we went to lower temperatures. So if we plotted the heat capacity, say in units of kB, versus temperature, that Dulong-Petit rule, 3N, goes like so. And experimentally, the data are going to look like that. So here's my little example of what experimental data might look like. And as noted last lecture, it is observed experimentally that at lowest temperature, the scaling is T to the third. So the fact that we see this deviation from the classical results strongly suggests that this is a quantum effect. Nevertheless, we know how to think about the very low temperature behavior of harmonic oscillators. They essentially turn into two-level systems. The corresponding energy for each mode then is just the average energy of a two-level system with an energy gap h bar omega for the alpha mode, which is independent, so I can study it independently. So this is the average energy for a single two-level system, or a single two-level system approximation to a harmonic oscillator, quantum mechanically, which has energy gaps, h bar omega alpha, and the corresponding heat capacity for a two-level system, beta h bar omega alpha squared times this Boltzmann factor, like so. So indeed, this has a non-trivial temperature dependence. Each mode has a non-trivial temperature dependence. But it by itself, it's not clear how it conspires to give rise to this experimentally cubic temperature dependence. So, as noted last time, the total heat capacity is a sum over all independent modes. So we can express the heat capacity in units of kB as an integral over those frequencies. The number of frequencies at omega times each's contribution to the heat capacity. So this G of omega times d omega is the number of modes between omega and omega plus, d omega. And so understanding that empirical temperature dependence really comes down to trying to understand how many modes there are with a given frequency. And so I want to just go over this argument again that Einstein and Debye had. Einstein he imagined that each particle in a lattice essentially fluctuated independently. So I pick one particle out. He imagined it had independent fluctuations, each of which with a single characteristic frequency. And if the system is made out of only one kind of particle, there's only then one characteristic low frequency, which was important. And consequently, his model for G of omega was then that there were just 3n numbers of those frequencies, all of which were at omega naught. And subsequently, the heat capacity would be predicted to then go a little too fast to zero. So in fact, this approaches zero exponentially. So again, qualitatively, this is correct. There's the fact that there's a discreteness in those energy levels quantum mechanically suppresses the heat capacity due to the suppression of fluctuations in the energy. I have to have a pretty improbable fluctuation to excite the energy and thus change it. And at zero temperature, there's no potential for that fluctuation to happen, so the heat capacity is zero at zero temperature. But the scaling, how quickly it goes to zero was a little over predicted. And so Debye subsequently fixed this model by imagining that particles undergo more collective vibrations. So the picture here, instead of a single particle oscillating in some cage, I look at groups of particles, for example, the whole system, undergoing some very low frequency oscillation. So the motion is smeared out over many, many unit cells, many, many particles taking place. Therefore, locally, the environment doesn't change that much, and subsequently, the potential change would be fairly low. So this would be some very long wavelength. Fluctuation, and we argued that there is empirically a so-called linear dispersion which relates the characteristic wave vector for that motion to its corresponding frequency. Now subsequently named so-called acoustic modes or phonons. And if there's a linear relationship between K and omega, knowing the density of K one would know the density of omega, and this then subsequently goes like omega squared. So in Debye's model, the heat capacity per Boltzmann's constant being still an integral over all the frequencies, now with some characteristic frequency omega naught. This can be integrated exactly, but it is sufficient to factor out just the temperature dependence. So if we do a U substitution, where U is h bar omega, and thus du is beta h bar d omega, we could substitute U and du in, and we'll have a beta h bar minus 1 out in front, and an integral over du, 1 over omega naught cubed, a u squared, a factor of beta h bar, inverse n squared, and this e to the minus u. That's just substituting those factors in. Accounting for all the factors of beta, I have one here and one here. This indeed goes like beta to the minus 3, or thus temperature to the plus 3. Okay, so again, I like going back through that calculation just because it is a pretty sophisticated application of these really basic notions of single particle partition functions and the energy that they are embedded with. So, it takes a couple steps to be able to do this sort of calculation. For a solid, one needs to recognize that at low temperature, there are small fluctuations about some average, and thus, in a vibrational or harmonic approximation of the potential is useful. That still gives you a set of potential which is interacting. So if we go back up here, here the potential, let's make that a little bit bigger. The potential here is not expressible as a sum of independent particle energies, because I have this I here and the J there. So they're coupled. So it looks like it's not going to be a tractable calculation for us to do because we don't know how to handle systems that are interacting. But a harmonic system is a special example where there exists some representation, some set of modes, which does decouple them. And so introducing these normal modes, or these phonons in the context of a solid, we recover a linear summation of the energy on independent variables, these complicated modes, thus forming our independent particle, yielding our independent particle form, which then can be simply evaluated either classically using equipartition or quantum mechanically by making some additional approximations associated with the very lowest temperature behavior. Okay. So that's an application to a fairly realistic system. Solids, this works really well for semiconductors, where it really is the lattice degrees of freedom which play a predominant role in their heat capacities. This does not work very well for metals, where we have to worry about really electronic fluctuations, owing to the fact that in a semiconductor, there's a big gap for an electronic excitation, so electronic energies don't fluctuate a lot, but in a metal, that's not true. There's a continuum of energies. And so actually one of the next lectures, we'll consider how we would add in electronic fluctuations to this description. But for the time being, I want to end today's lecture thinking about more realistic gases and what we can learn using our theory so far. So these are systems that exist in some dilute limit, so I can treat them as non-interacting. And let's just kind of build up in complexity from something pretty simple to something more complicated. So let's start by asking about an actual monotonic gas, argon. What is the constant volume heat capacity of argon gas? Let's have a little thought experiment whereby you really need this number for something. You're in the lab getting ready to run an experiment, and it would really be beneficial for you to know the constant molar heat capacity of argon. Maybe you're filling your vacuum chamber with argon, and you need to know exactly how much energy to supply in order to raise the temperature some given amount. And now let's imagine that Berkeley infrastructure being what it is, maybe your internet doesn't work, so you can't just look up this answer. So how would you go about using what we know to compute it? Well, argon, whether or not it's your little gas chamber or in the room, there's some argon in your atmosphere. It's essentially if it's dilute, a non-interacting particle undergoing some translational motion in whatever that confined space is. If that box is macroscopic, it's going to be reasonable to treat that translational motion, and this temperature is room temperature, it's going to be reasonable to treat that motion as classical. And if, therefore, there is only translational motion, well, we know how the energy for translational motion goes. That's just kinetic energy, 1/2 mv squared. But argon is complicated. There's a bunch of nuclear degrees of freedom. There's a bunch of electrons. Should we have to worry about describing them to compute the heat capacity of this gas? Well, to know whether or not it's going to contribute to the heat capacity, we need to know if those energy gaps are large enough for to be thermally excited. So delta E for, say, an electronic excitation for a argon atom. Well, what kind of energy scales, what kind of light do you need to shine on argon to excite its electrons? Do you see it fluorescing spontaneously? No, so electrons aren't going from some high energy state spontaneously to a low energy state. Indeed, in the wavelengths of lights are nanometers. That translates to order EV for typical energy gaps for electronic excitations, and 1 kBt at 300 NeV is a fraction of an EV. It's about 1/40 NeV, or 0.025 EV. So thermal energies are not going to generate electronic excitations. So if I only have translational motion, we already know what the answer to this is. The heat capacity is going to be, well, I have N atoms in some, or N molecules in some gas, N argon atoms in some gas. They have 3 directions that they can translate. Equipartition tells me that I get a kb/2 for each one of those dynamical degrees of freedom. So CV, if I wrote this in terms of R, where R, say, the per molar heat capacity, where R is NA times KB, is going to be 1.5. So that's our prediction. The molar heat capacity in units of the ideal gas constant is 1.5. Very simple number. That's our prediction. And now we can note that whether or not this was argon or helium, same for neon, simple atomic gases, the heat capacities would be the same for all of them. Well, is it right? So I just have happened to have pulled up a table here. So this is the molar heat capacities for common gases at near room temperature. And for argon, we indeed find the molar heat capacity is 3/2, also known as 1.5. And that is the same for something like helium. All right. Carbon monoxide, however, has a much larger heat capacity, very close to 2.5. Can we use what we already know to reason through that result? So if we were going to draw out carbon monoxide, I would have some carbon, imagine that's blue, and some oxygen, imagine that's red. So we just observed empirically that that was about 5/2 kb, or 2.5 molar heat capacity in units of the ideal gas constant. And we know that 3/2 of those is going to come from translational motion. Now, that gas, we have to be a little bit more careful about that, what we mean by translational motion. It's really how a single CO dimer moves around. So it's really the translational motion of the center of mass. Okay. So then where does the rest come from? Now the heat capacity, again, is a measure of the scale of energy fluctuations. So we have to have other ways by which carbon monoxide can fluctuate that argon cannot. So there are two likely candidates. Well, it has an intramolecular bond, so there could be vibrations. But for the energy to fluctuate, it must be the case that thermal energy is sufficient to promote vibrational excitations. Any of you listening, do you know what the characteristic frequency for a CO stretch is? That is about 2100 wave numbers. Again, kBt at 300 is something like 210. So that is very unlikely to happen. Okay, well, what else can CO do that argon can't? Well, it could translate, we account for that. It can vibrate. It can also rotate. What is a typical characteristic scale for rotational energy levels? Those are also quantum mechanical. Fundamentally, there is some discreteness to their scale. Turns out that rotational energy scales are on tens of wave numbers. So this is very possible at room temperature to contribute to the heat capacity. Now, we have not calculated a rotational partition function and thus understood how rotational degrees of freedom can contribute to the heat capacity, but I will assert that we don't actually have to do the hard calculation. We can infer what the result's going to be. So let's think about rotation. So I have my, say, carbon and my oxygen. Well, it can rotate in 3 space. So on the surface of some sphere. We just said that the vibrations are essentially really stiff. They're in their ground state. So I can imagine that this is maybe a rigid rotor. So I can rotate this in that direction or along the equator. So there are 2 ways that it can rotate. When I map this to a rigid rotor, I introduce an effective mass. Which is the mass of one times the mass of the other over the sum. If we imagine the bond length is fixed, and I've already convinced myself I can treat this classically, then the partition function for rotations is going to reduce to essentially the number of places I can put this effective particle on the surface of the sphere. In some effective resolution. So let's denote that bond length capital R, the number of spatial arrangements for this particle on the surface of the sphere is just proportional to the surface area of a sphere. That resolution is going to be informed by quantum mechanical fundamental limits, as well as being smeared out by some temperature. So just like translational motion, I can imagine that there's some effective length scale, some thermal length scale, which sets up the effective resolution over which I count those spatial positions on the sphere. If that's true, well, that's that resolution squared. We know translationally the effective resolution gives me a factor of beta to the minus 1/2. I get that squared, so I get a factor of beta to the minus 1. So essentially I have 2 components of angular momentum. Two spatial degrees of freedom that I can translate through. Now this is in some curved space, so it's not exactly the flat translational motion we've considered before, but there are essentially 2 independent motions for velocity to explore. In this case, they're angular motions. And then there's a surface of the sphere which counts up all the places I could put that particle. So if there are 2 angular momentum, if we did the calculation, would have given us quadratic variables. And thus CV for CO2 will have 3/2 from the translational degrees of freedom, and now 2/2 contributions from rotations. 2 factors of KB/2 for the 2 different harmonic angular momentum that this rigid rotor can explore. And that would be the same. The logic then is the same for something like diatomic nitrogen. In principle, it's the same for something like hydrogen gas as well. or oxygen gas? So do nitrogen, hydrogen, oxygen all have the same heat capacity as CO? Well, oxygen's pretty close. Nitrogen's not on here. Nope, it's pretty close. Hydrogen is smaller. That's kind of interesting. I wonder how we've overcounted there. Fluctuations in hydrogen relative to CO are suppressed slightly. How do we suppress fluctuations? Well, if we actually acknowledge that there was a discreteness to energy levels, that would be one way. So maybe there's something associated with hydrogen being light and therefore more quantum mechanical that we'd have to consider. That's a very reasonable hypothesis. Turns out not to be right. Okay, so that's the heat capacity game. We could get more exotic should we really want to. We could ask, for example, what about water? Still in the gas phase. So water, hydrogen connected to oxygen connected to two hydrogens. It has 3 translations it can undergo in its center of mass. How many independent rotations does it have? Well, I could rotate about that axis. I could rotate about that axis, or I could rotate about that axis. So there are 3 rotations. So we would predict that the heat capacity then has 3 factors of 1/2 kb for the translations, 3 factors of 1/2 kb for the rotations, thus giving us 3 kb. And that checks out. That's pretty much right at high enough temperature where the water molecules in the gas really don't interact. All right, well, that's all I really wanted to say. You are all diligently preparing for your midterm, I'm sure. I'm sure you haven't put this off till after you took the exam. So good luck, and I'll see you all hopefully in the live session on Thursday.